Department of Physics, PV Siddhartha College of Arts and Science. Today I am going to explain a very important concept which is essential to understanding quantum mechanics. The title of the concept is Postulates of Quantum Mechanics. Classically, we can describe any physical quantity in terms of coordinates, position coordinates and momentum coordinates. Remaining all other quantities are also expressed in these two representations only, position and momentum coordinates. But quantum mechanically, how a quantum state is described and how these physical quantities defined in a given state T. In classical mechanics, we have different approaches. At a time T, we can describe the motion of a particle in terms of position and momentum. At any later time T, the position of the particle can be described by Hamiltonian equations. Basically. So, but however, in quantum mechanics, the coordinates are replaced by operators. So the notation is different and also the applied principles also different. So the formalism of quantum mechanics is based on the postulates. These postulates cannot be derived. These are experimental results. Actually, we know in quantum mechanics there were three formalism. One is Heisenberg formalism, second one is Sekhar formalism, third one is Schrödinger formalism. In Heisenberg formalism, every physical quantity can be expressed, and everything can be expressed in terms of matrix mechanism. So the diagrams of the matrix represents the energy spectrum, which are discrete in manner. In Schrödinger equations, actually in Schrödinger derived two set of equations. One is known as Schrödinger time dependent wave equation. Other one is known as Schrödinger time independent wave equations. So instead of matrix mechanics, Schrödinger derived two second order differential equations. The solutions of the equations gives or represents the energy spectrum. But however, the results are equivalent. Matrix mechanism and Schrödinger results are equivalent. And Dirac expressed everything in bracket notations. The bracket notation also a simple mechanism. So instead of matrix and Schrödinger, we can use in some situations bracket notations. Everything can be expressed in bra and cat notations. So however, the formalisms in quantum mechanics purely based on postulates. There were four postulates in quantum mechanics. Five postulates in quantum mechanics. Number one, state of the system. State of the system. So in quantum mechanics, a particle or a system can be represented by a wave function psi, which is known as state of the system. So psi provides the information about the particle, which is a function of r comma t. R is a position representation, t is a time. So what is the significance of the wave function psi of r comma t? It is a new terminology. The wave function, the significance of wave function, which provides the dynamical information about the particle. Whereas in classical mechanics, you can express everything in position and momentum coordinates. So now, according to first postulates, assign a wave function psi to a particle or a system. Once if we assign this wave function to a particle or a system, second postulate is find the observables and the operators. This is the second postulate of quantum mechanics. Every physical measurable quantity is associated with the operator. Operator is a mathematical approach. It is a purely mathematical approach. In classical mechanics, generally we can use coordinates representations. Whereas in quantum mechanics, the coordinates are replaced by operators. The coordinates are simply replaced by operators. So in classical mechanics, generally the position coordinate is represented by x, momentum coordinate is represented by p, and also every quantity expressed basically in position and momentum representations. Whereas in quantum mechanics, the position coordinates, say the coordinates are replaced by operators, which is represented by x cap. Cap means operator. It is a mathematical approach. So the position coordinate becomes position operator. Similarly, momentum operator, energy operator, angular momentum operator, total angular momentum operator, spin angular momentum operator, parity operator. So everything in quantum mechanics can be expressed in operator mechanics. This is the second postulate of the quantum mechanics. First is the state of the system. Second one is the observables and operators. After choosing this suitable operator to the system, the third postulate is measurement of eigenvalues and eigenfunctions. This is the third postulate of quantum mechanics. So when an operator A is acting on a state vector. So the operator is the second postulate of quantum mechanics. State vector or a wave function is also known as eigenvector or eigenvector. It is the first postulate of quantum mechanics. So when this operator like A acting on a wave function psi of t gives an eigenvalues lambda in the state vector psi of t. This is known as eigenvalue equation. If any operator at A is operating on a wave function psi of t gives an eigenvalues lambda, the lambda represents corresponding eigenvalues. If the final state vector is same as the initial state vector, it is known as an eigenvalue equation. If the final state vector is not equal to initial state vector, it is known as not an eigenvalue equation. Eigenvalue equation, state vector, final state vector is equal to initial state vector. This is the third postulate of quantum mechanics. Once if we find the wave function, the motion of a particle at a given time t, now the fourth postulate is probability. Now what is the probability of the finding the particle in a volume element T2? Now let's say the state vector according to first postulate, choose the appropriate wave vector operator A. Now apply A on this psi of t, that is position representation, position operator and momentum operator, whatever it is. Then apply when you apply the operator and state vector psi of t, which gives an eigenvalue. So with the help of eigenvalues, now find the position of the particle or position of the system. So next, the fourth postulate of quantum mechanics is probability. It is known as the probability of the system. So it means it finds the particle position in a volume element T. So mathematically, the probability function P can be expressed as integral psi star of d tau. This is the probability density function. Here psi is a wave function. Psi star is the complex conjugate of psi. It is known as psi star psi is known as a probability of the function, probability of the system or probability of the particle. Psi star is the complex conjugate of psi. If psi involves any imaginary term, the sign of the psi changes in complex conjugate. If psi has only real values, there is no change in this complex conjugate. For example, if psi is equal to exponential ikx, then the psi star will be exponential minus ikx. The sign of the imaginary term changes. This is the mathematical representation of the psi star. Psi star is the complex complex conjugate of a wave function psi. Okay, so finds the particle position in given volume unit d2. D2 means dx, dy to dz, which is a three-dimensional transformation. Once if you find the state of a particle as a state of a psi in a given term d2, now what is the state of a system at any later time t? Then fifth postulate of quantum mechanics. The fifth postulate of quantum mechanics is known as time evolution of the system. So the first four postulates evolve in time. The first four postulates describe a quantum state at a given time t. The first one, state of the system, observables and operators, measurement of eigenvalues and eigenfunctions. Fourth one is in probability. The first four postulates can describe the state of the system at a given time t. The fifth postulate, time evolution of the system, can describe state of the system at any later time t. Classical mechanics, in classical mechanics, at any later time t, the motion of a particle or the state of a particle can be described by Hamiltonian equations. Hamiltonian derived two set of first order equations, popularly known as Hamiltonian canonical equations. Whereas in quantum mechanics, at any later time t, so psi at any later time t, psi after simply represented by psi initial into time evolution operator into psi of t initial. So this is constant time evolution operator. So at any later time t, psi of t can be expressed as time evolution operator into psi of t. Psi of t is the initial state vectors. So the fifth postulate describes state of the system or state of the particle at any later time t. Actually, these postulates are not derived. These are cannot be derived. These are experimental results. So the entire quantum mechanics is purely based on these postulates. There is no exception for these rules applicable everywhere in the universe. There are no exceptions for these rules. Simply first assess state of the system. Second, find observables and operators. Next, by using first and second postulates, measure the eigenvalues and eigenfunctions. Then find the probability. Because our aim is to find the state of a particle within the volume element d2, which is narrowly expressed as p is equal to psi plus d2. Fifth one is at any later time t, the quantum state can be described by psi of t is equal to time evolution operator initial state vectors. These are the postulates. These are the postulates in quantum mechanics. Okay, so in quantum mechanics there are different approaches purely based on these postulates. Okay, for example, in time evolution of the system, the Schrodinger time independent wave equation can be written as IH cut into rho psi of t by rho t is equal to h into psi of t. This is known as a Schrodinger time dependent wave equation. The Schrodinger time dependent wave is according to Schrodinger time dependent equation. The Hamiltonian operator h cap psi of t is equal to IH cut into rho psi by rho t, which can be written as E psi h psi is equal to E psi. When energy operator h psi is equal to E psi, when Hamiltonian operator h cap is acting as state vector psi of t gives an energy eigenvalue E. In quantum mechanics, energy E is known as energy operator, which is mathematically expressed by IH cut into rho by rho t. Let us see the energy operator. So Schrodinger time independent equation is h cap Hamiltonian operator h cap is acting as psi of t gives an energy eigenvalue with the same state vector. This is known as eigenvalue equation. Here the Hamiltonian operator h cap is simply expressed as minus h square by 2m that square psi plus e psi. This is the Hamiltonian operator concept. Sum of the kinetic and potential energy minus h square by 2m that square plus v. So when this Hamiltonian operator h potential is acting as A of P gives energy value, energy eigenvalue E, where E cap is represented as I expected to dou psi by dou pi. This is known as energy operator. Energy operator. This is known as Hamiltonian operator. This is about the postulates of quantum mechanics.